Okay, so now, so far what we studied is that we applied the momentum equation and we calculate the forces involved. Now we consider moving vanes. Next we consider here the moving vanes. Vanes are in motion. So in this case we consider the concept between absolute and relative velocities. Earlier we saw that whenever we calculate the forces, we have a velocity diagrams here. For example, in this case, the velocity is horizontal. And in here you see that the velocity makes an angle theta. Similarly, we can have a vane where the velocity fluid enters here with the velocity makes an angle theta. You see here now it will have two components, and similarly the fluid leaves this vane, it will have two components. It will have two components here. So now in this case, if the vane is stationary, so we can easily resolve these into components, and we consider now that the vane is in motion. So then in this case we have to consider the relationship between the absolute and relative velocities. So we can have any possibility of these triangles which are shown here. We can have any possibility of these triangles. First we define what is the absolute and the relative velocities, and then using these triangles how we calculate the relationship between these three types of velocities. For example, we have a body A, and this body is moving with a velocity of 100 meter per second. These are moving with a velocity of 100 meter per second. This is, let's say, body 1. Another body, which is, let's say, body 2. So this body, this is moving with a velocity of 60 meter per second. It is moving with a velocity of 60 meter per second. Clear? So now you can see that what is the relative velocity between these two bodies. So the relative velocity will be the difference of the two. This will be the relative velocity, that will be 40 meter per second. So the relative velocity of first body with respect to second body, that is 40 meter per second. Clear? So now in this case, you see that when we consider the motion of these two bodies, we have to also consider their relative velocity. So this is how, when the vane is moving and the jet of water will strike the vane, then in that case we have to consider the absolute and the relative velocities. So first we defined them, what is the relative velocity, and then in that case, let's say for example, this is the velocity of the first body, and the second velocity of the second body is denoted by u, and we will use a small case letter here, v, to denote the relative velocity. Then in this diagram you can see here that v1, that is equal to u plus the relative velocity here. v1 is equal to u plus the relative velocity. This is now the relationship for a linear system. You see here that this is the relationship, that this v1 will be equal to u plus the relative velocity. Now if we have a situation where these triangles are formed, any of these triangles in here, So then in this case, what we have v1 is equal to u plus small v. What will be the relationship here? That we need to establish. Then we will be able to calculate the forces. Clear? So first we define the relative and absolute velocities, the angles that make, and then we can establish the relationship between the three velocities. So the absolute velocity v of a body is its velocity relative to the earth. So what is the absolute velocity? The absolute velocity of a body is its velocity relative to the earth. So the body is moving at 100 meter per second with respect to earth. So this v1 that we write down here, that will be the absolute velocity. Similarly, the second body is moving with 60 meter per second. So that is the absolute velocity with respect to the earth. But then what is the velocity of the first body with respect to the second body, the relative velocity? So that is the relative velocity. That is 40 meter per second in this example here. So the relative velocity small v of a body is its velocity relative to a second body, which may in turn be in motion with absolute velocity u relative to the earth. So the relative velocity of a body, it is the velocity of a body relative to a second body. And the second body may in turn be in motion with absolute velocity u with respect to the earth. So this is the definitions of the absolute velocity and the relative velocity. Now the absolute velocity of the first body is the vector sum of relative velocity to the second body and the absolute velocity u of the latter. This is what I show you here. For a linear system, then what we have is that the absolute velocity of the first body, that will be a vector sum of the relative velocity plus the absolute velocity of the second body. This is for a linear system, so this is easy. V is equal to u plus small v. This is small v, to differentiate from the nu which we use for kinematic viscosity. So this is small v that we use for relative velocity here. Now in this case, if we have any of these triangles, these are the possibilities which can come. As I said, that when a fluid enters into a plate or blade or vein and it leaves, and also the blade is in motion with respect to u. Clear? So then in that case the relative velocities will come. So that relative velocities we have to consider. So these triangles which will form here and the triangle that will form here for a vein or blade in motion, so any of this case can occur. This can be case 1, any of this case can occur. Similarly, this can occur depending on the given situation. Similarly, we can have this case 3. So now when we have these cases, how you establish the relationship between the three velocities? Before we try to establish the relationship, then in this case you can see that these are the angles which the relative velocity and the absolute velocity can make. The second body will translate in this direction, so that is u. This is u here. This will not have any components. This will be a translation. Clear? Only we can make an angle with u, and the relative velocity can make an angle with u. So we define these two angles, that alpha and beta, these are the angles made by absolute and relative velocities of a fluid respectively with the positive direction of linear velocity u of some point on a solid body. So now we have that the second body, which is a blade or vane, that will move with a linear velocity u. U will not make any components. Clear? Because the body will translate. So that is only in this direction. Now we have the absolute velocity of the first body, which makes an angle theta here, and the relative velocity, which makes an angle of beta, both with the direction of this u. So if we have this case here, or this case, or this case, it says that parallel to u, the relationship is vu in the u direction is equal to u, which is in the u direction, into the relative velocity in the u direction. So this will be equal to v cos of alpha equal to u plus small v cos of beta. V cos of alpha is equal to u plus small v cos of beta. Parallel to u, this will be the relationship. And perpendicular to u, so perpendicular to u, this will be equal to Vn is equal to the small vn, the relative velocity. This will be the same. So it means that v sine of alpha will be equal to v small v sine of beta. So now in the parallel to u means in this direction, and perpendicular to u means this direction. This will be the relationship between the three velocities, because perpendicular to u there is no component of u. There is no component of u perpendicular. So that's why what we can say is that v cos of alpha is equal to u plus small v cos of beta, and this is equal to v sine of alpha is equal to small v sine of beta. So it says that for all cases, when we have all the cases or all shapes of triangles, you will have this relationship. This relationship is true for all the cases. This relationship is true for all the cases. So now let us prove that this relationship, whether we have this case, whether we have this case, or whether we have this case, you will still get these components. So let us see how we get this. I will do it for two cases and then you can verify for the third case. So let me try to do it for the two cases. So now what we do is that let us consider the first case. So in the first case, we have this as the component of small v, and this is the vertical component of small v. So it makes an angle of beta. Similarly, for this v here, this is, let's say for case 1, we work on case 1. And this will be the component of v. You can see here, this is the horizontal component of this v, and this will be the vertical component of this v. So you can see here, this component, it will be v sine of alpha, and this component here, this will be equal to v cos of alpha. Similarly, for small nu, this component will be equal to small v, that will be equal to sine of beta, and this component here, this will be equal to small v cos of beta. So now you can see, if we want to calculate parallel to u, so you can see here that parallel to u, in this direction parallel to u. So what is this? We have this v cos of alpha. This is the component parallel to u. This is equal to this u. This is u. This component is equal to this is u. So this is equal to u, and then this here. So this will be equal to plus small v into cos of beta. Now perpendicular to u. So perpendicular to u, what are the components here? So perpendicular here, this is perpendicular. So in this case, you can see these two components are same. From here, from this triangle, you can see these two components are same. So we say that we sine of alpha, that is equal to small v sine of beta. There is no component of u in the vertical direction. So that's why you can see this is the situation. This is how the relationship between two comes, parallel to u and perpendicular to u. This is what we saw earlier here. You can see here v sine of alpha is equal to v sine of beta, and v cos of alpha is equal to u plus v cos of small v cos of beta, u plus small v cos of beta. So this is how we get for case number 1. Now next we come to case number 2 here. So now in this case number 2, what is the relationship? Let's say I now consider this as case number 2. So in this case now we consider here these triangles. So now u is this angle here, this can be 180 minus beta, 180 minus beta. This is alpha. So you can see that in this case we will have the two vertical components here. So what will be the relationship? Let's say I consider parallel to u. So parallel to u in the u direction, what is the situation? We have v, this will be equal to v cos of alpha, v cos of alpha, clear? So this will be equal to u, up to here is u. So we have u is here, from here to here this is u, up to here this is u. So u, this is u, and then this component is now opposite, considering the angle 180 minus beta. So this will be equal to minus small v into cos of 180 minus beta. This will be equal to cos of 180 minus beta. Now what is cos 180 minus beta? So you already studied that cos of alpha minus beta. In your college you studied that cos of alpha minus beta. So this is equal to what? This is equal to cos of alpha into cos of beta plus sine of alpha sine of beta. Sine of alpha into sine of beta. Now that alpha is 180 degree. So sine 180 degree is 0. This is cancel out. Sine 180 degree is 0. And then cos of 180 is minus 1. So cos 180 is minus 1. So minus cos of beta. From here now it is minus cos of beta. So now we have minus cos of beta. So this will be equal to u into minus into small v into minus cos of beta. This is equal to minus cos of beta. So minus into minus plus, what we get is v cos of alpha, that is equal to u into plus small v cos of beta. U plus small v cos of beta. So this is the component which is parallel to u. And if you see here, this is the same component. You see v cos of alpha, that is equal to u plus small v cos of beta. You get the same result, parallel to u. Next we consider perpendicular to u. So then perpendicular to u. Perpendicular to u now in the vertical direction. So what we have? We have v sine of alpha. So this will be equal to v sine of alpha. There is no component of u in the vertical direction. So this will be equal to, for here, what is the situation? Small v into sine of 180 minus beta. Sine of 180 minus beta. Now you already know that what we have in this case, we already know that we have sine alpha minus beta. So what is this equal? This is equal to sine alpha sine beta, sine alpha into cos of beta, clear, minus cos of alpha into sine of beta. So now that alpha is 180 degree, so you see sine of alpha, this term is 0. This term is 0 and cos of 180 is minus 1. So we have minus 1 into sine of beta. So now this will be equal to small v into minus is plus. So this is equal to what? It means this will be equal to sine of beta. So this will be equal to sine of beta. So you see v sine of alpha, that is equal to v sine of beta. This is what we obtained earlier. If you look here, you can see here that v sine of alpha is equal to small v sine of beta. This is what we obtained here. So now the conclusion is that whatever is the case, we will get these relationships for all the cases. You can see here that whatever is the case of triangle, this relationship is the same. That's why for all cases, for all shapes of triangles, we have these components of the velocity here. So you can verify yourself for case 3. You will get the same result. You will get the same result. So now this is the relationship between the 3 velocities when we consider the relative velocities and absolute velocities. Now we come to how we can calculate force of a jet on one or more moving vanes or blades. So first we consider a single blade which is moving parallel to the jet. We consider a single blade which is moving parallel to the jet. So now you can see here that we have this single vein and it is moving with a velocity u. You can see here it is moving with a velocity u. So it is translating in this direction. So the vein is moving, but the velocity is less than the velocity of the jet. So that's why the jet will be able to reach and it will hit this vein or blade. And we can calculate the force. So in this case, you see the velocity is more. The vein is moving, it is translating with a velocity u. The velocity v is more. You see here, this is v, as shown in this diagram here. And the vein moves with a velocity u. So that's why there is a relative velocity between the two, which we denote by small v. So this is your v, v1, and this will be your relative velocity v1 at the inlet, and this is u. U has just in horizontal direction only moving translation. So in this case, that's why we can write down this v1 is equal to u plus small v1. This is at the inlet. At the exit, you can see this triangle will form. That's why we studied here that depend on the given condition, any of this shape can occur. So that's why how we make this triangle here. How we make this triangle? You see here that if there is no vein, this is the absolute path which the jet will follow. This is how it will look to the observer. This is the absolute path. So this is the absolute path. That's why at exit, we have this absolute velocity v2. And to complete the triangle, this we slide here and we bring it here. And we show this velocity v2 and it makes that angle alpha 2 with u as we shown the angles here. Alpha 1, alpha beta 1. Here what is alpha 1? 0. Because in the same direction as u. What is beta 1 for small velocity, relative velocity? That is also 0. But at the exit, they make an angle thetas. At the entrance, these are 0. But we can have entrance of the jet where these can have values other than 0. So now this is the absolute path. You see here, this is the absolute velocity at exit. This we bring here to complete the triangle. And to the observer, since the water flows over the vein, this will be the relative path. This is the relative path. As the water flows over the vein, this is the relative path here. That's why it is written here, the relative path. So this is the relative path which it follows over the vein here. So that's why relative path shown by the relative velocity v2. And it makes this angle beta 2 with the direction of u. So this is how we can make the inlet velocity diagram and the exit velocity diagram, and then we can calculate the forces. So before we calculate the force, we should remember that there are two major differences between the jet of water which is striking a stationary object, which we saw here earlier. In this case, we solved an example here, a stationary vein, and if a vein is in motion. So there are two major differences between these two. What are the two differences? The first is that the amount of fluid that strikes a single moving vein in any time delta t must be different from that which strike a stationary object. It means that, for example, we have this vein here and it strikes. If it is stationary, so let's say this is v1 and in here we have the area a1. Let's say area a1 is the area of the jet. So what is the discharge which is hitting this vein? If it is stationary, what is the discharge? a1 into v1. This is the discharge which it is hitting the vein, and multiply by the density. So this is the mass flow rate. So this is the mass flow rate which it is hitting. This is equal to rho q. This is equal to rho Q. So this is hitting. It means that whatever is the discharge coming, it is hitting the stationary vein. But if the vein is in motion, then this discharge cannot hit the vein, but it will be less than that. Clear? I will show you how it is less than that. So the first thing is that the discharge that will hit the vein, so this hit this vein, it will be different than the discharge that will hit the stationary vein. And the second difference is that for a moving vein, we consider the concept of relative and absolute velocities, which make delta V difficult to calculate. Delta V very easily in the problem we saw that delta V very easily we can calculate, but if the vein is in motion, you see that we have these complex triangles here. Either this can form or this can form or this can form. So determining the change in velocity becomes difficult. So these are the two differences that come when the vein is in motion. Now, how we calculate about the discharge? As I said, that the discharge that will hit the moving vein, it will be less. So if the cross-sectional area of the jet A1 and the velocity is V1, then the rate at which the fluid issues from the nozzle in terms of mass is this. This is the mass which will hit the vein. But if the vein is in motion, if the amount of fluid that strikes a single moving body per unit time will be less than this, clear, will be less than this when the body is moving away from the nozzle. When the body is moving away from the nozzle, then in that case the discharge hit will be less than this value. It will be less than this. Why? Because you see that we have this vein and it is hit by the velocity A1 and V1, and then it is moving with U. So it is moving this velocity, it is hitting this velocity with A1 V1, the discharge, volume flow rate A1 V1. But now that this vein is moving, so it means that after some time the vein will be here. Let's say in U distance, 1 second, U is equal to S is equal to Vt. Okay, clear? For here, S is equal to Ut. So now in 1 second, so S distance covered will be U. So it means that it covers this U. Clear? So now it covers this distance U, and the velocity is more because it is able to hit. So the velocity is actually more than this. It is this actually the velocity V1. So now you can see that if the vein moves from this point to this second point, then some of the discharge will be used to elongate. Previously it was hitting at this position 1 here, but now the vein has moved to position number 2. So it means some of the discharge will use to elongate the length, and the remaining will hit the vein. So what will be the remaining? V1 minus U. This is now the remaining. Multiply by the cross-sectional area A. This will now hit the vein, or in other words, we can write down A into small v1, because this is the relative velocity. So it means now this is the discharge that will hit the vein. Clear? If the vein is at rest, so it is hitting the vein with A into V1. This is the discharge it hits. But when the vein is in motion, some of the discharge is used to elongate and remaining will hit. So what is that? This is the discharge, either V1 minus small u into A or A1 into relative velocity. This will hit the vein. Of course, if the vein is moving with a velocity u, so if and the jet is striking the vein with velocity v, if u is equal to v, if the vein is moving with the same velocity as the jet will not strike the vein. So in this case, force will be 0. And if the velocity of the vein, it is greater than or equal to v, If it is, let's say, greater, equal, we already consider. So let's say if the velocity of the vane is greater than the velocity of the jet, then in that case it will never hit this vane. Then the jet will never hit the vane. So only the case is that when u is less than v. In this case, the jet can reach the vane and it can hit the vane. So that's why the discharge, when it is hitting a single moving vane, it will be less than this value. It will be less than this value. How much less than this value? Equal to v1 minus u times a. This will be equal to rho into v1 minus u, because blade is in motion, into a 1. It will hit with this, and this is less than this discharge. It is less than this discharge. Clear? If it is moving with a velocity of u less than that of the jet, as I explained, less than that of the jet, the amount of fluid that strikes the body per unit time will be proportional to the difference of velocities between the two. You can see here the difference of velocity between the two. It will be proportional to that. So it means that instead of capital V1, we have to consider the difference of velocity in the discharge that will actually hit the moving vane. So now instead of that, actually it will be q dash, and q dash is a1 into v1 minus u, where v1 is the absolute velocity of the jet and this is the velocity of the vane. So this is equal to a1 into relative velocity v1, because from here this v1 minus u, this is equal to the relative velocity small v1, and the mass flow rate, that will be equal to a rho into q dash. The mass flow rate, that will be equal to rho into q dash. Consider the relative velocities. Now in the equation, what is the equation? If a single moving vane and the discharge is hitting that vane, so in that case we have summation of fx, that will be equal to rho and q dash, not q, but a discharge less than the case where we have the blade is at rest. So it will be rho q dash. Next, the important thing is the change in velocity. So now this change of velocity, how we calculate? Using this triangle, we already know the velocity that we discussed for the three cases. Whatever is the case, you can easily calculate the change in velocity by these components at the inlet and at the exit to the vane. So in that case, now the thing is that this change of velocity will be the change of absolute velocity or relative velocity. This will be the change of absolute velocity or it will be the change of relative velocity. Which one you have to consider? So it says that from here, in the u direction, we say that the change of absolute velocity, this is a very simple proof. You can consider this triangle, this relationship at the inlet between the three velocities, and this triangle here at the exit, and from here you can prove that delta v is equal to small delta v. It means that in the u direction, the change of absolute velocity will be the same as the change of relative velocity. So it means that in this equation, when we have a single moving vane, so the force in the u direction that you calculate, you consider absolute change of absolute velocity or you consider change of relative velocity, you will get the same result. You can consider the change of absolute velocity to calculate the force, or you can consider the change of relative velocity, you will get the same result. So that's why in calculating the force for a single moving vane, the discharge will be q dash less than the q, and the change of velocity in the u direction, that will be either you consider the absolute velocity or you consider the relative velocity, you will get the same answer. So now that we know the basic concepts, so we can then easily solve a problem. Clear? So for a single moving vane, this summation of forces, this will be equal to rho q delta q dash delta v or rho q dash delta small v. Change of absolute velocity, this is relative velocity, or change of absolute velocity, you will get the same answer in the u direction. Clear? So summation of forces in the u direction, that is equal to rho q dash into change of absolute velocity in the u direction or change of absolute velocity in the v direction. If we consider rho is equal to gamma by g and q dash is equal to a1 into small v1, the relative velocity, so force of jet on a single moving vane or blade, that can be given by this equation. So this equation we can use to calculate force of jet on a single moving vane. So now the single moving vane, practically it has very little significance, that we have just a single moving vane, it is moving and it is the jet of water, it is striking, very little practical wave. It can rarely occur. So that's why we are more interested on a series of moving vanes. This is important case and more practical case. Force of jet on a series of moving vanes. So then in this case, as I said, that a stream of fluid which is striking a single moving vane, clear, rarely occurs. So what we have, the more common case is that the jet is directed as a series of closely spaced rotating vanes. For example, of a turbine, Pelton wheel. So you can see here that in this case, the water is supplied to the turbine here, and you see these are the vanes or blades, the rotating element of the turbine. Clear? The rotating element of the turbine. So the vanes are located at the periphery. The water is issued from this nozzle here. This is the nozzle, and it strikes these vanes and pushes them in the u direction, and as a result this wheel rotates. As a result this wheel rotates. This is an example of Pelton wheel, impulse turbine. So as a result of this wheel rotates, and then this wheel converts, this turbine converts this hydraulic energy into rotating shaft mechanical energy. So to this is connected a shaft which you can see perpendicular to this slide here. So when this wheel rotates, it rotates the shaft. So this is due to impulse of this water. That's why this is known as a turbine. Clear? So this turbine converts this hydraulic energy into mechanical energy in the form of rotating shaft, and then we have generator, and generator converts that mechanical energy into electrical energy. So this is what happens in hydroelectric power plant. But anyhow, the thing is that a single moving vane is not very important case. It rarely occurs. Rather, we are interested on a series of rotating vanes or blades. That is a more practical case. And this is not only for a turbine. This is also for a pump. You might have seen the rotating element of a pump. It also has the vanes or blades. But in this case, the turbine takes the energy of the flowing water, but in case of pump, it adds the energy to the flowing water. But in both the cases, the forces are involved. So now in this case, how to calculate the force? It says that in such cases, when the water is striking a series of moving vanes or blades, whatever the flow that does not strike the first vane, it will strike the second vane, and so on around the circle. What we said earlier in the first case, that in this case, if we have a single moving vane, so the discharge that is hitting is less. because the vein is moving, not full momentum is transferred. The vein is here and then it comes here. So you see that some of the discharge is used to elongate and then the remaining hits. So that's why the discharge was reduced. Instead of Q, we have Q dash. For a single moving vein, the discharge hitting the vein was reduced. But now in case of a series of moving veins, it says that this vein, when it is moving, when it moves in this direction, the next vein will come in this place. So it means that if any fluid which is not striking the first vein, if it misses the first vein, it will strike the second vein, and so on. So it means that for a series of moving veins, we are fully utilizing the momentum transfer rate. So it means that we do not have Q dash, but we have Q. It means that the water which is striking a series of moving veins, that is fully utilized. The momentum is fully transferred. The water striking is not reduced, because even if it misses the one blade, the next blade will come and it will be hit by that discharge. So that's why when we have a series of moving veins, so this discharge is fully utilized. So we can express the U component of the force exerted on a series. You see here, in this case, we are only interested that what is Fu, what is the force exerted on these veins in the U direction. So that's why for a turbine, we always calculate this force. There will be a force in vertical direction. There will be a force in vertical direction perpendicular to you. That will be perpendicular to you. But we are not interested in that. What we do with this force? We are just interested to calculate how much this force is exerted so that the momentum is transferred to the turbine, rotating element. So it will have a vertical component, but we are not interested in that. That's why for us, such type of cases, normally we do not calculate the vertical component of the force. We only calculate in the horizontal, in the U direction, in the direction of movement of the vein. So that's why you see we can express the U component of the force on a series of vein as this. So when we have a series of veins or blades, then in that case it will be the mass flow rate, but it will be rho Q, not Q dash. You can see here Q is A1 V1, not reduce. And we can consider the change of velocity, either the absolute or the change of relative velocity. You will get the same result. So now what is the difference between a single moving vein and this is the basic equation. Now if you want to calculate the force, this is the basic equation. So it was earlier we applied this rho Q into delta V. Now for a single, this is for the previous we applied on the structures on the stationary veins. But now if a vein is moving, so for a single vein, what we studied is that for a single moving vein, moving single vein, let me write down here. How you calculate this? We said that for this will be equal to summation of forces. That will be equal to rho Q dash. And change of velocity, you can consider absolute velocity or relative velocity. You will get the same result, UQ dash. Because a single moving vein, some of the discharge will use to elongate to reach to the moving vein, and then the remaining will hit. So the discharge hitting vein is reduced. And for a series, if we have a series of moving veins, so then in that case this F, this will be equal to rho Q, not Q dash, rho Q into delta V. And you can consider change of relative velocity or change of small velocity. This is relative velocity you consider or absolute velocity you consider, you will get the same result. So this is the difference. Clear? Now let us solve this problem to what we have done so far to better understand how we use this concept. So now in this case we have a jet of water that is 2-inch in diameter. We have this jet of water 2-inch in diameter here, and it is the jet of water, it is moving with a velocity of 100 foot per second, and it strikes on a single moving vane. Now we have a single moving vane in the same direction at a velocity of 60 foot per second. So the vane is moving with a velocity of 60 foot per second, and the jet of water is moving at 100. So you can see u is less than v, so the jet can reach and it will hit. If u was 100 or more than 100, then the jet of water cannot hit this vane. It cannot reach this vane, it cannot hit this vane if u is greater than v. If u is greater than v1, then jet of water cannot hit. So u must be less than v1 in order for jet to reach and hit the vane. So u is 60 foot per second, and the jet of water is moving with a velocity 100 foot per second. Now as this water flows over the vane, so due to the friction the velocity will reduce. So you see here that this vane, it will move, this is the absolute path. So the absolute path, you have this v2, this is the absolute path. If there is no vane, this is how the jet will move. So that's why this v2 we show here. We slide this vector and we show, and this is the angle alpha 2 it makes with u2. And because this is the relative path, this is how to the observer it will appear. This is the relative path. That's why we have this relative velocity, and it makes this angle here beta 2 with the u. This is beta 2. So this is how we can make, because here it enters tangentially in a horizontal direction. So that's why the inlet velocity diagram is this. This is the inlet velocity diagram, and this is the exit velocity diagram. You have to make these inlet and outlet, inlet or exit velocity diagram in order to calculate the forces. This is important. So now let us proceed. So the first part is that the V2, the small V2, it is 0.9 times V1 due to the friction losses over the vane. So due to the friction losses over the vane, V2 is equal to 0.9 times V1. Now the question is compute the net force of water on the vane. And if this vane, one part B is one of a series of vane, how much is the horsepower transferred? So first we calculate the net force for water over this vane. Clear? The velocity vector diagram at entrance and exit are given here. I already showed to you. Now V2 is equal to 0.9 times V1. This is given here in the question. So now in this case, V2 is 36 foot per second. Now we want to calculate, because we have to calculate the change in the velocity. So that's why we calculate what is V2 in the u direction, the exit velocity V2. So we already know that this is the relationship, whatever is the shape of triangle. Clear? Whatever is the shape of triangle, we already saw that this is the relationship in the u direction between the three velocities. So now we are using those concepts here in the problem. You see that what we studied here, in here, that's why we studied here, because in the problem you need them. Whatever is the shape of triangle, these will be the relationship parallel to u and perpendicular to u. So that's why in that direction, here you see V2 cos of alpha 2 will be equal to u plus small v2 cos of beta 2. So now all the values are known, and this is the V2U. Next, we consider the normal component of that V2. This is the normal component to U. So in that case, we already saw that V2 sine of alpha 2 is equal to small v2 sine of beta 2. So this is the value of the velocity V2 in the normal direction, normal to U, normal to U, normal to this direction. Now we can calculate Q dash. Why we can calculate Q dash? Because we have a single moving vane. We have a single moving vane here, a single vane moving. So that's why you will need to calculate Q dash. And this will be equal to A1 into V1 minus U, or A1 into small v1, the relative velocity. So you can put the values, and this is the discharge that will hit a single moving vane. Now we consider the forces here, and we consider plus x and plus y. These are the assumed direction of the forces in the x and y direction. These are assumed direction. In the end, the plus minus sign will tell us that these directions are correct or not. So these are the assumed directions. Clear? These are the assumed directions here. So this is minus fx opposite to this. This will be minus opposite to plus y. So remember, minus x and then minus y. No other forces are acting. No other external forces are acting. So we consider only fx, fy, and rate of change of momentum. So we consider minus fx into rate of change of momentum in that direction. So we already calculated these, and you calculate minus 120.4 pounds. So now from here we get the value of fx is equal to 120.4 pounds. Fx is equal to 120.4 pounds. So I get plus answer, because this minus cancel out with this minus. This minus cancel out with this minus. So it means that this assumed direction, which was in this direction, you see, we have this vane, and we assume fx in this direction, on this vane. This direction is correct. And we consider fy in this direction. So it means this direction is correct, because you get plus minus, plus sign. If I get minus sign, then this direction you have to reverse. So what will be the force of, this will be the force of vane on water. The force of water on the vane will be to the right. What will be the force of vane? So the force of vane will be opposite, equal and opposite to this. It will be to the right. This will be the force of water on the vane, equal and opposite to this force. Next we calculate Fy, that will be equal to rho q dash and change of velocity in the y direction. So this is equal to, again minus minus cancel out, so it means this direction is correct. What will be the force of water on the vane, equal and opposite to this? This will be the force of water on the vane, equal and opposite to this force Fy. Now we have the two forces, we can calculate their resultant. So what will be their resultant? This will be their resultant here. This will be the resultant of the two forces. And we can calculate its orientation. Using Pythagoras theorem, we can calculate the resultant force. So we can, Fy is now here, assumed direction is correct, clear. So the force of water on the vane will be equal and opposite to that. And now the net force of water on the vane or blade or vane, that is equal to this. So what will be the net force? This we calculate using Pythagoras theorem, 124.2 pounds from Fx Fy. And this is the angle theta that you can calculate. So what will be this force here? It will be this force acting equal and opposite to this force. It will be this force here. This will be the total force. This will be the force of vane or blade. Let me write down blade. this will be, sorry, this will be the force of water on the blade. This will be the force of water on the vein or blade, and this will be its orientation that we can calculate from these components. So that's why you can see here, this is the force of water on the blade and it is making this angle. So we have this force, and if this is alpha, so you can see that this is also alpha. Clear? This is force of, resultant force of water on the blade or vein. If this is for a single vein, if we consider a series of veins, then what will be the difference? For a series of vein, we have to calculate Q, not Q dash. We don't have to calculate Q dash, no. But we have to calculate Q, because for a series of vein, the whole momentum transfer occurs. If any vein misses any discharge, the second blade will come and it will be hit by that discharge. So the momentum transfer is full. That's why we need to calculate Q, not Q dash. So now we need to calculate Q. So Q will be equal to A1 V1, and this is the discharge that will hit a series of moving vein. What was the discharge that hit a moving single vein? Q dash. So a discharge that is hitting a single vein, that is Q dash 0.873 CFS, cubic foot per second. But if we consider a series of moving vein, you can see 2.18 CFS. So now for a series of moving vein, we are interested to calculate FU. So that's why we only interested to calculate Fx. So that will be equal to rho Q into change of velocity in the x direction. So you plug in the values, you get this value. So minus and minus cancel out. Minus and minus cancel out. It means the assumed direction is correct. There will be Fy here. There will also be Fy. But for series of moving vein, as I show you here, in this Fy we are not interested. We are only interested in Fu because it will rotate this vein. This is what we are all interested, that how much force is transferred, how much power is transferred. So in the vertical direction there also will be component, but we are not interested to calculate. So that's why we only calculate this Fx. Clear? And we are not interested to calculate Fy, but there will be Fy. So now what is the power transfer that we have to calculate? So power is just F into U. So the power that is transferred to the blade is moving with a velocity U. So your force will be just Fx into U. So that will be the power transferred from water to the veins, and divide by 550. So we can calculate this power transferred in horsepower. So this is how we apply the momentum equation to calculate the forces on a single moving vein and on a series of moving veins.